Alright, let's now talk about moment of inertia. As we saw before, net torque divided by moment of inertia is equal to angular acceleration, just the same way that net force divided by mass of the object gave us the linear acceleration. Now the moment of inertia of an object which has a mass m and is rotating about a rotation axis which is marked by x, and the moment of arm here is r, and let's say the rotation is counterclockwise, then the moment of inertia is simply given by this expression, I is equal to r squared m. That's for a single mass m, which is connected to the rotation axis via a rigid massless rod, let's say. Now what if we have an extended body? So there's more than one mass. So in this picture here we have m1, m2 and m3, and I'm going to go ahead and mark the rotation axis. Our rotation axis in this case is on the plane of the paper, so let's say the rotation occurs like that, about the rotation axis. What the moment of inertia of this extended body is now given as the sum of each individual, the moment of inertia of each individual mass, which you can calculate by using this expression. So it's the sum of the moment of inertia of m1, moment of inertia of m2 plus moment of inertia of m3. To calculate the moment of inertia of mass 1, you need to know the moment of arm for mass 1, which is the perpendicular distance from mass 1 to the rotation axis. Similarly, r2, the moment of arm for m2, is the perpendicular distance from m2 to the rotation axis, and r3 is a perpendicular distance from m3 to r3. So you need to figure each moment of arm carefully, and then use this expression right there to calculate the net the total moment of inertia for the extended body. If you have a rigid body, then the sum notation of course takes the form of an integral. In the textbook, the methodology for using the integral technique to calculate the moment of inertia is introduced. I'm not going to go into it in these lectures because we will not be using the integral form in any form or fashion in this course, but nevertheless, if you're interested, do browse through the chapter. It's an interesting technique that you will need to master for higher courses in physics. Now, using the integral technique, one can then go ahead and calculate the moment of inertia of a solid disk. A moment of inertia for a solid disk is equal to 1/2 of mr squared, where m is the mass of the disk and r is the radius of the disk. This is the moment of inertia of a solid disk. If you have a thin hollow loop or hoop, thin hollow hoop, then the moment of inertia is simply mr squared, where m is the mass of the hoop and r is the radius of the hoop. Needs to be a thin hollow hoop though. Now the moment of inertia depends on the rotation axis, so the moments of inertia that I've given here are for rotation axes through the center of the disk and also through the center of the hoop. Now if you have a solid sphere, as this case right here, then the moment of inertia is equal to 2/5 of mr squared. There's in the text the moments of inertia for different objects through different rotation axes is listed. You do not need to memorize these expressions. If you can, that's fine, but you don't have to. Come exam time, the moment of inertia of for a given shape through this particular axis will always be given to you to use, so you don't have to memorize these, but it's a good idea to learn a few anyhow. The most common ones that are used are disk, a hoop, and a sphere. So here is a sphere, solid sphere. So let's take a look at a dumbbell. We have a dumbbell which consists of two masses, mass M connected via a rod which has a total length of 2L. Alright. And in the first case, this is scenario 1, let us consider the rotation about the center point. So the rotation axis is actually this line here. So this is how, let's say, the rotation is going to occur. And actually the way I've drawn the force here isn't quite correct. So now let's say there is a force F which is being applied. So F will be tangential, let's say, to trying to draw a three-dimensional drawing. I hope you can follow. I apologize if it's not too clear, but that's the best I can do. And in scenario 2, the rotation axis, let's say, is through one of the masses, the mass on the right hand side, and we apply the same force. So let us consider the angular acceleration that we have in scenario 1 versus angular acceleration in scenario 2. Well, we need to calculate moment of inertia for scenario 1 and moment of inertia for scenario 2. Remember, we're talking about the same object, same extended object, but since the rotation axes are different, then we may have two different expressions for moment of inertia, two different values for moment of inertia. So you cannot assume that moment of inertia remains the same. Now, and for each case, we also need to calculate the torque 1, scenario 1, and torque 2. Now we know that torque is torque 1. Torque is the product of moment of arm, which the radial distance r times the tangential force. Okay, and we also know that the moment of inertia is the sum of mi r squared, and we'll also make use of the fact that alpha is net torque, or torque divided by moment of inertia. So these are the three expressions we're going to use. So let us consider the moment of inertia for scenario 1, I1. We have ml squared plus ml squared, which is 2ml. So this is for the mass on the left hand side, moment of inertia of the mass on the left hand side, plus moment of inertia of the mass on the right hand side, which is equal to 2ml squared. Now moment of inertia in scenario 2, well, mass 2's moment of inertia is 0 because, well, not mass 2, I'm sorry, the mass on the right hand side, because the perpendicular distance of this mass to this rotation axis is 0. Therefore the moment of inertia of the mass on the right hand side is 0. So we only have moment of inertia due to mass on the left hand side, and its moment of arm is 2L. So we have m times 2L squared, which is 4ml squared. So you see that moment of inertia in scenario 2 is twice as much as moment of inertia of scenario 1. So I2 is equal to 2I1. Now let us consider the torques in each scenario. Torque 1 is FL, simply the tangential force. I said that F was tangential, times moment of arm. And torque 2 is F times 2L, because our moment of arm is twice as long. So here you see that torque 2 is equal to twice torque 1. So even though in scenario 2 we have twice as much torque, one would expect that we'll have the same angular acceleration because our our moment of inertia is twice as much as scenario 1's moment of inertia. Since torque is equal to I alpha, then alpha 1 is torque 1 divided by I1, and alpha 2 is torque 2 divided by alpha 2, i.e. that is alpha 1 is equal to alpha 2. So in each case we end up with the same amount of angular acceleration, since even though the value of the torque doubled, since the moment of inertia doubled as well, the angular acceleration remained the same. Now, if you know an object's moment of inertia through its center of mass, so this is ICM, if you know that, which you can calculate. So if you calculate, let's say, the center of mass of an object, then depending on the orientation of the rotation axis, you can go ahead and calculate the moment of inertia through any axis through center of mass. Now, if the object, if you're interested in finding the moment of inertia through an axis, a rotation axis, which is parallel to a rotation axis through through the center of mass of the object, but is displaced by distance d, then we use the parallel axis theorem, which states that the moment of inertia of an object through this blue rotation axis is equal to moment of inertia of the object through its center of mass plus the sum of the product of each mass times I apologize, I had to interrupt the recording for just a second. Anyways, I was saying the parallel axis theorem states that the moment of inertia through an axis which is parallel to one that passes through the center of mass is equal to moment of inertia of the object through the axis that passes through the center of mass plus the sum of the masses times d squared, where d is the perpendicular distance from center of mass to the rotation axis of interest. Alternatively, of course, you can calculate I for this blue rotation axis by simply figuring out the radial distance from each mass to the rotation axis. So we have mi r1 squared, m1 r1 squared plus m2 r2 squared plus m3 r3 squared, of course. So that's if you know the radial distances, but if you don't know the radial distances, but you do happen to know the moment of inertia through the center of mass of the object, then that's a simple calculation. This parallel axis theorem provides simple means to calculate the moment of inertia. For example, if you let me see what I have here. Instead of the potato that I've drawn, let me go ahead and draw a sphere. All right. We have a sphere. Now we know that the moment of inertia for a sphere through an axis through its center of mass is 2/5 of mass of the sphere times radius of the sphere squared. Okay, so now the moment of inertia for the sphere through the green rotation axis here, which is parallel to the blue rotation axis through its center of mass, however, is displayed by amount d, is given by ICM plus mass of the sphere times d squared. So it's 2/5 of mr squared plus md squared. That's the moment of inertia for the sphere rotating about the green rotation axis, which is a distance, the perpendicular distance d, radial distance d away from the sphere's center of mass. So if you know the moment of inertia for a rotation axis, moment of inertia for an object about its rotation, about its center of mass, then it's a simple, very simple calculation to use. Um, it's one of the equations that may be useful to have on your equation sheet come exam time. Okay, I'll talk about equilibrium in the next lecture.